Welcome to Dealing with Noise. So one advantage of a Fourier transform spectrometer is that it allows signal averaging of multiple spectra to improve our signal-to-noise ratio. So note that a signal spectrum contains a good deal of noise. In this case, we've got a good deal of noise here. An easy way to measure noise is to measure the range of noise on our baseline. So that's over here. We've got, say, 9 units in this case, and our signal in this case happens to be 14 units. And our signal then can be measured from the middle of the noise on the baseline to the middle of the noise on the peak maximum. The middle of the noise on our baseline is there. That's this value here. The middle of the noise on our peak maximum is there. And that difference then is our signal, which is 14 units in this case. And that means that our signal to noise ratio is our signal 14 divided by our noise, which is 9, which in this case is 1.6. And so if we average together multiple spectra, then the noise is going to tend to cancel out, but our signal will tend not to cancel out because our signal should be there in every spectrum, and so we're essentially multiplying our signal. So if we have 256 here, you can see a nice clean spectrum compared to our spectrum with just one. A more common, but also more complex way of determining noise is the root mean square noise, or RMS noise, that we calculate this way, where AI is the signal from the ith data point, A bar is the mean signal, and N is the number of data points that we have. If the number of data points is large, then the RMS noise is the standard deviation of the data points. The RMS noise is about 5 times less than the peak-to-peak noise that we used earlier. And that means that the RMS noise is roughly 9 divided by 5, which is 1.8. And our signal-to-noise ratio is then about 7.8. So clearly, the signal-to-noise ratio depends on how you're measuring the noise. And this means that comparisons of signal-to-noise ratio for different spectra must therefore use the same method of noise measurement. When n spectra are added together, then the noise is increasing by a factor of root n, but the signal is increasing by a factor of n. And that means that the signal-to-noise ratio is increasing by a factor of root n. And thus, in order to improve the signal-to-noise ratio by a factor of 2, we must use 4 times as many spectra. And to increase by a factor of 10, we must use 100 times as many spectra. It's generally not worth averaging more than about 10 to the 4 to 10 to the 5 spectra, because instrumental instabilities will cause drift over time, and that will tend to spread the width of our peaks. So there are 3 common types of noise. We've got white noise, or Gaussian noise, which we show up here. We've got drift, or 1 over f noise, which we show here. And we've got line noise, or interference, which we show there. So let's look at white noise, or Gaussian noise. One source of white noise, called Johnson noise, arises from random fluctuations of electrons in an electrical device. So naturally, we can reduce the Johnson noise by reducing the temperature of our device. Another source of white noise, called shot noise, arises from the quantized nature of charge carriers and photons. That is, if the signal is very low, then random variation in the small number of incoming photons or generated electrons and holes in a semiconductor causes noise. The second type of noise here is drift, or 1 over f noise. The 1 over f noise scales with the inverse of frequency. That's where that f is coming from. So that means at its highest at 0 frequency, and is decreasing as frequency is increasing. One example of this is flickering or drifting of a light source or a flame, in the case of atomic spectroscopy. And these can arise with slow changes in instrument components with temperature, age, and variation in the power line voltage. Now, drift can often be corrected by periodically measuring the standard and correcting for any observed change in the signal. Our third type of noise is line noise, or interference, shown down here. So a peak at 60 Hz is likely due to interference from the 60 Hz transmission frequency of alternating current electricity, at least in the US. Other portions of the world use different frequencies. And interference can occur from other sources, such as movement of people and equipment throughout a building. Now, electrical shielding, grounding the shielding in the instrument to the same ground, and physically isolating the instrument can help reduce the interference that we see. Another technique for reducing noise is called beam chopping. So a chopper alternately sends light through the sample and the reference. and this allows both cells to be monitored nearly continuously and allows for noise reduction. Beam chopping moves the analytical signal from zero frequency to the frequency of the chopper, and thus 1 over F noise and line noise can be minimized by chopping. And that was dealing with noise.